Have you ever thought about what it would take to teach a computer common sense? Like really, truly, how to understand the world in all its messy, unpredictable glory?
It's a fascinating challenge, right? Because traditional logic systems with their black and white, true or false approach, they just don't cut it when it comes to real life.
Exactly. The world is full of gray areas, exceptions to the rule, things that logic alone just can't quite grasp. And that's where Markov logic networks come into play. MLNs for short.
Ah, yes, MLNs. Think of them as a way of giving AI a dose of that real-world pragmatism. They combine the power of logic with the flexibility of probability.
So instead of saying, this is always true, an MLN might say, well, this is usually true, but
Great. It's like that old saying, never say never. There are always exceptions, and MLNs are designed to handle those exceptions gracefully.
and that's what makes this whole approach so exciting, so potentially groundbreaking. In a way, it's like we're bridging that gap between how computers traditionally think and how we as humans navigate the world.
Absolutely. And that has huge implications for the future of AI. We're talking about everything from smarter recommendations to breakthroughs in scientific research.
Okay, so we've piqued your curiosity. Now let's dive into the details and unpack what makes MLNs tick. We're going to be referencing a fascinating academic paper for this deep dive, by the way. And the first thing to understand is how MLNs combine logical rules with weights that reflect their real-world probabilities.
It's kind of like baking a cake, actually. You have your recipe, the instructions, which are like the logical rules in an MLN, but then you have the freedom to adjust the ingredients, the quantities to create slightly different flavors.
So the weights in an MLN are like adjusting the volume knob on each rule, turning some up, some down, based on how likely they are to hold true in a given situation.
Precisely. And that ability to fine-tune the recipe is what makes MLNs so adaptable, so capable of dealing with the complexities of the real world.
So we're talking about formulas, weights, constants. It feels like we're laying out the ingredients for some kind of AI potion here.
And in a way we are, but instead of eye of newt and wing of bat, we have things like logical statements and probability distributions.
Sounds a lot less spooky, I have to say. So let's break it down. What exactly are these formulas?
Well, think of them as the backbone of the MLN. They're the logical rules that govern how different concepts relate to each other. It's like saying, if A, then B, or if it's raining, then the ground is wet.
Okay, so pretty straightforward so far. But the real world is rarely that cut and dry. Right? Things aren't always true or false. Sometimes it's more like, well, if it's raining, the ground is probably wet.
You're getting it, and that's where the weights come in. They allow us to quantify those shades of gray, those degrees of uncertainty. So instead of just saying, if A, then B, we can say if A, then B with a probability of, say, 80%.
So it's like we're assigning a confidence score to each rule.
Exactly. The higher the weight, the more confident we are in that particular rule. And these weights can come from various sources. Expert knowledge, statistical analysis of data, you name it.
And that brings us to our last ingredient, constants. What's their role in this whole MLN recipe?
Well, the formulas and weights give us the general framework, the rules of the game, so to speak. But to apply those rules to a specific situation, we need to plug in some actual values, some real-world data, and that's where constants come in.
So if we stick with our rain analogy, instead of just saying the ground, a constant might be a specific patch of ground, like your backyard.
Precisely. Or it could be a specific time of year or a particular type of soil. These constants allow us to ground the abstract logic of the MLN in concrete examples.
And that grounding, that connection to real-world data, is what makes MLNs so powerful, so capable of making accurate predictions.
Exactly. It's not just theoretical anymore. And to illustrate that, let's look at an example from the paper where they apply MLNs to a real-world data set. They used information about students and faculty at the University of Washington's Computer Science Department to predict student-advisor relationships.
Oh, that's the academic matchmaking project. I remember reading about that. So how do they do? Were the MLNs any good at playing matchmaker?
Surprisingly good, actually. They fed the MLN information about who published papers with whom, who took classes from whom, that kind of thing.
So the MLN had to sift through all those academic connections and figure out who was most likely advising whom. Right?
Exactly. And they compared the MLN's performance to other prediction systems. Some of these other systems were based purely on probability, ignoring the logical relationships altogether.
And I'm guessing the MLN came out on top.
It did. It significantly outperformed the other approaches, demonstrating the power of combining logic and probability in this way.
That's really impressive. But before we move on to other applications of MLNs, I want to circle back to something you mentioned earlier, first-order logic being a special case of MLNs.
Right. It's a bit of a technical point, but an important one to understand. You see, first-order logic is great for representing absolute truths, but it struggles when things get a bit fuzzy.
Because in first-order logic, it's either all or nothing, right? No room for exceptions.
Exactly. It's like saying all birds can fly. It's a nice, neat statement, but it doesn't quite reflect reality, does it?
Not at all. Penguins, ostriches. They might take offense to that.
Exactly. And that's where MLNs shine. They allow us to say most birds can fly, or birds are likely to fly, acknowledging that there are exceptions without throwing out the entire rule.
It's like MLNs have a more nuanced, more realistic view of the world, which is essential when you're dealing with messy, real-world data.
And because of that, they're able to make more accurate predictions, even when the data is incomplete or noisy, which, let's face it, is most data in the real world.
So we've seen how MLNs can play matchmaker in academia, but the paper hints at a much wider range of applications. What else can we use these things for?
Well, that's where things get really interesting.
Okay, so we've covered student-advisor matchmaking, which is pretty neat, but yeah, what else? The paper mentioned some other uses for MLNs, right?
Yeah.
Oh, absolutely. In fact, the potential applications are incredibly diverse. For instance, one area that's really promising is fraud detection.
Oh, that's a big one.
Yeah.
Especially these days with online transactions and all that.
Right. And because MLNs are so good at handling uncertainty and those shades of gray, they could be really good at spotting those subtle patterns that might indicate fraud.
So instead of relying on hard and fast rules, which can be easy to circumvent, the MLN could learn to pick up on those subtler cues that something fishy might be going on.
Exactly. It's like giving financial institutions a sixth sense for sniffing out scams. And then there's the whole field of personalized medicine.
Okay, now that sounds super futuristic. How would that work?
Well, imagine being able to feed an MLN all sorts of data about a patient, their medical history, their genetic makeup, their lifestyle choices, and then use the MLN to help doctors tailor treatments more precisely.
So it's like using AI to create a custom treatment plan for each patient based on their unique circumstances.
Precisely. It could help doctors predict potential risks, identify the most effective interventions, even suggest preventative measures.
That would be revolutionary. But are we talking about something that's like decades away? Or is this something that could realistically happen in our lifetime?
Honestly, some applications of MLNs are closer than you might think. I mean, they're already being used in things like image recognition and natural language processing, which are fields that are advancing incredibly rapidly.
True, true. So looking ahead, it seems like the sky's the limit for MLNs. What would you say is the key takeaway for our listeners today?
I think the biggest takeaway is that MLNs represent a fundamental shift in how we're approaching AI. It's not just about brute force computation anymore. It's about building systems that can reason and learn and adapt in a way that's more akin to how we humans operate in the world.
And that's incredibly exciting because it opens up a whole new realm of possibilities for what AI can do.
Absolutely. I mean, there are always challenges, of course, and we have to be mindful of the ethical implications. But the potential for MLNs to help us solve complex problems, improve our lives, it's truly immense.
Well said. And that's a wrap on this deep dive into the fascinating world of Markov logic networks. We hope you enjoyed this journey into the cutting edge of AI. It's been a fascinating conversation, and we always appreciate the chance to geek out with y'all.
Yes. Thank you for listening.
Don't forget to check out the show notes for links to the paper and other resources. And until next time, stay curious.